Hello everyone, I'm Chen Yuwang from Alibaba Group, and today I'm glad to share our work with you entitled Making Pre-trained Language Models End-to-End Visual Learners with Contrastive Prompt Tuning. Okay, so we can see pre-trained language models have been very popular nowadays, and if you give an NLP application, you can simply fine-tune a pre-trained language model to support the application. However, there is a requirement that a sufficient amount of training data is needed for downstream tasks, which means we should label the training data and send to the model for fine-tuning. However, the labeling process is very tedious, and sometimes we simply don't have that resources to label this data. So prompt-based fine-tuning can be used to fine-tune the visual language model better. And to the simple, we have two basic elements. The first is called prompts. Prompts are fixed templates or patterns that are employed to inject specific guidance to the input text. And the other one is called verbalizers, which are explicit mappings between the output and the class labels. Here I provide a very simple example for sentiment classification. For example, we have the text, a wonderful movie in every aspect, and we add a simple prompt. It is a mask token. So if the model predict the word can be good, so wonderful movie in every aspect, it is good. So it is a positive review. While if the model predicts it is terrible, it means it's a negative review. So we simply change the classification task into a mask language modeling task. And previously, we have showed that prompt-based fine-tuning significantly improves the performance of burst-down models if we have very few training data. And in the right, we can see some experimental results. However, one thing we need to remember is that we need to manually define the prompts and verbalizers, and the change of prompts and verbalizers affect the performance to a large degree. So the performance might not be very stable, and it is sometimes difficult to tune the model to ensure good performance. And in our work, we introduced a new solution called contrastive prompt tuning, or CP tuning. In this framework, we don't need to manually define the task-specific prompts and verbalizers. So it's more automatic and can achieve better performance. In the right, we have the framework. So we have a pre-trained language model. Instead of have a CIS token for classification, we have two types of new tokens. One is called the T-mask. The other one is called O-mask. T-mask is for the auxiliary mask language modeling task, while O-mask is for the output token. So we don't have these task specific prompts, and we don't have these verbalizers. Instead, we have a contrastive learning based task to make the final prediction. Okay, and first, I'm going to introduce task invariant prompt encoding. So we have three types of specific tokens. The first is PRO, it means prompt. This is a placeholder for our continuous prompt embeddings. And the rest, the remaining two tokens are T-mask and O-mask. So given a classification task, either it's single sentence task or sentence pair task, we simply add these prompt tokens to the input and finally place an O mask to the end. For example, if the input is movie fans get ready to take off to the other direction. So the input to our model is moving T-mask. Here, the fans is selected randomly. So this will need to be masked. Get ready to take off the other direction. So at the end of this sentence, we add three prompt tokens. The first two is initialized by the universal prompt called ATEs. And during the model training stage, it can be updated as well. So the we don't need to write manually defined prompt anymore. We just add some general words here, and finally there's the O mask. So the O mask is used to make final predictions. So this is a task invariant input template. So after we have designed this template, we can solve nearly all the common NLP tasks for birth style models. So next we have the verbalizer-free class mapping. Here we utilize the contrastive learning to do the mapping instead of defining verbalizers. For example, for sentiment analysis, we have the two verbalizers, good and terrible. We map good and terrible to positive or negative labels. This is a verbalizer-based approach. In contrast, we simply take the embeddings of the O mask to make the prediction. So we do not need to explicitly define which is the word for positive and which is for the negative. Simply, we compute the within class and between class similarities. So giving the embedding of the O mask. So we simply compute the inner product since they are already normalized. So this is equivalent of computing the cosine similarity. And we compute the sample-wise contrastive loss, which need to know that we maximize within class similarity while minimize between class similarity. Okay, in this case, we make the representations of the O mask similar if the two data instances are of the same class. If they are dissimilar, they belong to the different classes. So it is quite straightforward to define the sample-wise contrastive loss. And however, there are some problems with the original contrastive loss. For example, in the right-hand side, we can see the margin. So the margin there is no constraint on the margin. So if the margin becomes larger, the model will be more robust because there is a large margin between the representations of positive examples and negative examples. So the model would definitely to be better. And another problem is that we only minimize the distance of positive examples. So all the positive examples are pushed to a very small and very dense region. So the generalization ability of the model is likely to fail. So we define a new loss called pairwise cost-sensitive contrastive loss, and looks this way. So you can see it on the screen. So we define two pairwise relaxation factors. It makes some relaxation between the pairwise similarities, either within class or between class. So you can see that M is the margin factor. So it makes some relaxation. We don't necessarily need these positive examples to stay in a very dense region. In contrast, we need to improve the generalization of our model. And after defining the PCCL, and we have a mathematical proof that PCCL has a very close relation to the triplet loss, and with only one positive and negative example. So in the talk, we'll omit these mathematical details. And the PCCL loss is also related to the unpaired loss with one positive and multiple negative examples. Our loss is an extension to previous work. So if you're interested, you can check the proof and analysis in the paper. And finally, our loss function is the combination of the contrastive loss, PCCL loss, and the auxiliary mask language modeling loss. It's a linear combination with the coefficient called lambda. And finally, during model inference, we compute the O mask embeddings with the class prototypes. And finally, we have an argmax operator. So if an input instance, we simply calculate the O mask embedding. If it's more similar to the positive class prototype, then we determine it is a positive instance. And if it's more like a negative instance, so we assign the label to the instance. So you can see the entire workflow. We do not assign specific prompts or verbalizer to this any specific NLP task. We treat them equally and uniformly. So in the experiment, we have experimented our approach over 8 public NLP datasets, including a variety of tasks. And we do few-shot fine-tuning with K equals 16, which means in each class we only have 16 training examples. And we have two backbone. One is Robota. It's very similar to BERT and a little bit stronger. Another backbone is Albert. They're both very common and popular. So this is the overall model performance. We can see that for both Robota and Albert, our method outperform previous approaches. And here also some application study. We can see that both our task invariant prompts and our verbalizer-free approach contribute to overall model performance. And here are some visualization and parameter analysis results to see that the instances between different classes are well separated. Okay, and finally, let's end this talk with a simple conclusion. So we propose a CPU tuning framework that enables visual learning without defining any task-specific prompts and verbalizers. And we have achieved good results, outperforming all the previous state-of-the-art methods. And in the future, we'll extend our framework to other NLP tasks and combining CPU tuning with transformative learning technique to improve the model performance in low resource scenarios. And thank you all.